Okay, good. So let's try to measure the value of a resistor. So we do it like this. We put the multimeter in a range. Let's try to put it like this, 20 kilo ohm. Maybe just a second. Okay. So 20k, 20 kilo ohms. And let's take one resistor. So which one? I have this one. So you see there is a color bar on it. Some color bars, actually 4 of them in this type of resistors. So the one on the right is brown in my case, then black, orange and gold. So if you go on Google and you Google for resistor color codes, you will find a table that will enable you to decode a number which is the value of the resistance. So in this case, for maybe it's better if I switch it like this. For this resistor I have here, brown means 1, black means 0, so 1 0 is 10, and then the third line, which is orange, means 3, which is a multiplier, which means 10 multiplied 10 to the 3, which makes 10,000 ohms or 10 kilo ohms. The brown, the orange, the gold stripe has a meaning which is the meaning of the tolerance of the value of this resistor respect to the nominal value, which is indicated by the first 3 stripes, and this gold means 5% of tolerance. It means that if we measure the true resistance of this device, it will be something in between 10 kilo ohms minus 5% of 10 kilo ohms and 10 kilo ohms plus 5% of 10 kilo ohms. So why it's like this? Because of manufacturing reasons. So it's not possible to have a perfect value of resistance. So depending on the technology they use to fabricate this resistor, they have different values. This is a carbon-based resistor and it's not very precise. If you want to have a more precise resistor, you can buy of different types, like metal-based resistors. They will have a different color with the stripes, and then also sometimes they will have instead of 4 bars for the colors, they will have 5 bars of the colors. So you can find the meaning of these colors just by googling for a resistor color code. So I suggest you to try to find in the kit you have this type of resistor, so brown, black and orange, and then we will measure, we will make some exercise of measuring the resistance. So another thing which is interesting with this type of resistor is how do you know where do you have to start reading the code, from this side or from this side. It's rare, but sometimes it happens that the gold is also put at the beginning. Most of the time gold is at the end of this color code. But somebody told me many years ago that if you read it backwards by mistake and you compute the value, and if this value is bigger than 27 megaohms, then it means that you're reading it wrongly. But most of the time the gold is indicating the tolerance, so then you know which is the first color to be read. So Let's make another exercise. For instance, let's take another resistor like this one. So according to the color code, hope you can see, this is yellow, purple, red and gold. So the gold is the last one, is for the tolerance. Then yellow means 4, purple means 7, and red means 2. So this is a 47 multiplied 10 to the 2 is 4,700 ohms, or 4.7 kilo ohms. So this is how it goes. Then you can have other things, but let's focus on the resistor for the moment. So if you take this, then you can also remove these caps. So sometimes it's useful to have them like this, sometimes like that, in case you don't want to these things to touch other things in the circuit. For instance, here we have a circuit which is what I will ask you to mount during this course. You see, it's populated with many components. Sometimes you want to access a part of a component without touching the others, so it's useful to have these protections. Not all the multimeter have them. Now I just want to remove them, and then I take one resistor like this. Let's see if it is possible to see the multimeter. Okay, so if I take the resistor like this and I grab it together like this, then I can measure a value which is not exactly 10 kilo ohms. So if I push more with my hands, you see that this value is decreasing. So why it's like this? Because this is not the correct way to measure resistors. Because also my body has a resistance. And if I hold it like this, then the resistance of my body goes in parallel with the resistance of this device. So in fact, I can try to measure the resistance of my body by putting my hands like this. You see, it's not possible to measure it because it's bigger than the scale of I put on the multimeter. So let's try to put it like this and let's see what we can have. Nothing. So let's try to increase the value like this. Okay, here I can start seeing something. It's 0 point something, so the value is unstable because it depends the way I touch the tip of the probes. So if I touch them very gently, it's nothing, but if I make a better contact, you see that the value is getting lower. So let's say it's around 0.5 mega ohms, and this scale will set. If you are sweating or if your hands are soaked by, for instance, the conductive gel, so this resistance will be lower. So we always have to consider this fact when we are touching components, that we are short-circuiting things with our hands. They are not insulator. The resistance of a body usually is between 300 kilo ohms and 1 mega ohm, something like that, depending on the conditions. So this is why we are not measuring the correct value of this resistor. But let's try with this other resistor, for instance, which is 4.7 kilo ohms. So then I move back this to this range, and I hold this one like this. What is this? Ah, sorry, it's another resistor. I took another one. So this one is even better. So you see, I was expecting 4.7 resistor, 4.7 kilo ohm, but it's 0.1 something in this range. So to see it better, I move it in this range, 2 kilo ohms. Now that I understood that it has a different value. Okay, and then I can even move it to this lower range like this. So 200 ohms range. And if I do this again, then I measure its value. It's 118 ohms dot something. So this time, if I push harder, nothing changes, or let's say it changes very little. Why? Because the value of this resistor is very low compared to the equivalent resistance of my body. So my resistance is huge respect to this one. So if I put a very big resistance in parallel to a very small resistance, due to the law that we studied for the combination of parallel resistors, the equivalent resistance basically is very similar to the lowest one. So this phenomenon of short-circuiting things with our hands is basically important when we are touching things that has a resistance which is comparable with the resistance of our body. If the resistance is lower, basically our body doesn't alter too much the value of the things. So in case, just to be precise, you can put the thing on an insulating surface like this, like I have this plastic blue pad, and then you can more carefully touch it like this. So this is the correct way to measure resistances of components. Another practical thing, you will notice that basically all multimeters has a sort of groove here. You see this thing, which sometimes is useful if you want to put the terminal of the component in it, so you will hold it better. You see? Put it here. It will hold it better. Then there is another button here, which is this hold button. Sometimes it is useful because maybe you have many things or you are touching I don't know, with one hand something, and then you are not able to read what is the reading on the display, so you just push hold and it will hold the last value even if you disconnect this. So let's try to do this for a moment, and so this thing is useful. So let's say I'm doing such kind of thing. Now I changed the resistor, so I try to switch. Okay. Now the resistor is the same. I was just touching bad. Okay, now I push hold, then I can remove and I can read the value. It's just a simple memory. So another thing which is interesting is doing this check. So you can touch the leads together, and if everything is correct, this multimeter should display 0. So now this thing is not displaying exactly 0, because maybe this multimeter is not very precise. There is a resistance between the wires. Sometimes, let's see if it works, you can reset the 0 value. If you turn off the multimeter, you put them together, and then you turn it on. Okay, Okay, in this case, this multimeter is not doing this, but in many multimeters, if you do this procedure, you can reset the proper value to 0. So also, according to a table you might have about the accuracy of this instrument, which is, let's say, not a very I mean, it's a low cost thing. It is possible that the value that it displays is not exactly the true value, let's say, it measures. As every instrument, it has its own tolerance. Okay, so measuring resistances is quite simple. We say, unless the fact that if we want to measure very big values of resistance, we have to take care about this resistance of the body. Then another very popular thing we can measure is the voltage. So here, let's try to use this battery. So now we have to take care. We have to carefully select the voltage function, and specifically not to put the current ampere function if we want to measure a voltage, because if we want to measure a voltage and we set the current function, we will blow the fuse. Why? Because it will try to measure the current of a circuit having no resistors. So this battery, if you make a short circuit, because it's a battery and we say that the job of the battery is to maintain the voltage, whatever is the resistor you put between one pole and the other one, so it will try to maintain the voltage even if you put a short circuit, and then it means that by the Ohm's law, so the voltage across a resistor is R multiplied I, which means that the current I is the voltage V, now the battery, divided the resistors, and if you divide something by something very small, it makes a very big number, and then this will blow the fuse in the multimeter. So the multimeter has an internal resistor which is ideally 0 when you measure the amperes, and ideally infinitive when you measure voltage. So you have two sets of voltages, one with this symbol, so kind of two parallel lines, or one line with 3 dashes, so which is the symbol for DC current, and the other one with this sinusoidal things, which is the symbol for the alternate current. So this standard is just remembering you that this is high voltage in this range, so it's dangerous. So now we have a battery, so I'm going to this voltage. I verify that I have the black terminal in the common and the red one where we have the voltage, so not here, which is for amperes. So this outlet is also for current, but now I carefully selected the dial knob to voltage, so now this thing is set to measure voltage. And if I go like this and I put the leads like this, then I will measure almost 9 volts. So this is a fully charged battery. If I switch the terminals, maybe you see it better like this, it might happen that you will see minus something, like now. This minus just means that you reverse the polarity of the leads. So for instance, in this 9-volt battery, this hexagonal pad is the minus and the round one is the plus. So in all multimeters, the red terminal is the plus and the black is the minus. So if I put red on the plus and black on the minus, I have the correct sign. If I do like this, Then, because of the minus in the multimeter, I'm discovering that I measure it, the voltage the other way around. So I can discover the polarity of what I'm measuring by reading the sign. And this is important because when you want to connect something to a circuit, you don't want to switch the wires from one polarity to another one, because most of the times you can't reverse the polarity, especially if you are working with microchips. They are designed to work only with a certain polarity, otherwise you will destroy them. So it's important to check that the plus goes on the plus and the minus goes on the minus, so everything you have in the circuit that you are building. Okay, so another useful feature is this one. So all multimeters have it. So you see there is this symbol of Siren, like a loudspeaker, sometimes appearing also here. So it's basically an ohm meter. So you measure resistance, but if you touch, it will make a beep. It will not make a beep if I touch it with my hands. So I am putting a resistor of around, let's say 500 kilo ohms. It will not sound. But if the resistance is low, like 0 in this case, it will sound. So this is very useful, for instance, if you want to check if a wire, electric wire, is broken or not. So you have this acoustic cue. Okay, so let's say that for the moment these are the basic function of this tool: voltage and resistances. Maybe we will also use the current. So at the moment I turn it off to save battery. Okay, so let's continue seeing what we have in the kit. So in the kit you have a sort of wooden plate, and you can take advantage of this. So you will find some screws and bolts here. You can mount your Arduino like this. Maybe if you don't have the screwdriver, you can also use your hands to put these bolts like this, bolts and nuts. So the idea is to have a board where you have the Arduino here, and this little breadboard, you can put it here by peeling the scotch tape which is on the opposite side, and you put it like this. If you do this, you will be never able to remove it, so consider if you want to do it or not, because it's very difficult to remove this thing attached with this scotch tape. Is very strong, so I do it because I like to have it like this, but it's up to you. Okay, then another thing you will find is this long cable with this crocodile or alligator clamps. So it's like this. This is something that I prepared specifically for this circuit. And then what we can try to do is to try to follow the schematic diagram we have on KiCad. Or if you have other questions before we continue with the schematic diagrams, feel free to ask me. So if something is not clear with all this thing, or if you have some curiosity you want to ask me, so please feel free of doing it. So
I think give us just like 2 or 3 minutes so that we can put our Arduino board on the...
You want to put the Arduino board on the...
Yeah.
Okay. Okay, so that's a good idea. Then meanwhile, maybe that you do this, I can continue with the description of some very basic components that you can find. So here in this box will not use them during this course, but a very popular component that you can find are these things. These are LEDs, so light emitting diodes. So they come in different colors. Some of them are transparent, but they might be photodiodes, which means that they are diodes. They change their conductivity according the action of the light impinging to a sensitive area like this, while these others are diodes that will be illuminated when you put some current in it. So let's try to do a test. So if I take my multimeter and I put it in the diode function, put it like this, then I can check if this diode is working or not. So now, in order to do this better, I carefully spread a little bit these legs like this. I put one terminal like this, the other like this. Okay. So you see the multimeter is saying that nothing, the resistance is infinitive, but then I can try to flip it the other way around. Okay. And still we don't see anything, but maybe if I do this in front of the camera, you see that when I touch it, the light turns on and off. So what I'm doing is I'm touching the leg. If I flip it the other way around, now it never turns on. So why? We understood during the theoretical part of the course that diodes can conduct electricity only if they are forward biased. So if the polarity is connected in a way that the plus goes to the anode and the minus goes to the cathode. So what's going on now in this circuit? So how the multimeter can measure the resistance? So inside the multimeter, when I put it with this function, there is a source of voltage, so a battery, the battery of the multimeter that you mounted, connected to a resistor, and the multimeter knows the value of that internal resistor. Then you close the circuit with something. If current will flow, then the same current will flow in the internal resistor of this multimeter, because it's a series circuit, and if the multimeter knows the value of these resistors and measure the voltage across its internal resistors, then by using the Ohm's law it can calculate the current flowing in it. Simultaneously it can measure the voltage across this thing, the two probes, and by measuring the voltage across these two probes and knowing the current, it can calculate the resistor across the two leads here. So this is how the multimeter measures the resistance. In practice it measures voltages. So it's an indirect measurements. So now this thing is not measuring anything, but let's try to measure another type of diode that you should have in the box, which is this diode. So it comes in this package. There is a bar here which is indicating the cathode. So the anode is like this, and then I connect this. And now you see that the multimeter is measuring something 0.634. So what is this thing? So this thing is the so-called built-in voltage of a diode. So when we studied the diodes, we said that once we assemble the P and N junction of a diode, there is a migration of charge. So once this thing is manufactured in the factory, between the P and N part of the diode, and this builds up a voltage, which for silicon diodes is around 0.7 volt, which is exactly what we are measuring here, 0.6 something like that. So this is telling us that this diode is working. If I flip it, I see nothing, because this diode is reverse biased now in this condition. And why I'm not able to measure the same thing or something similar with an LED diode? It depends on the multimeter. Some multimeters can, some others cannot. It depends on the fact that the built-in voltage diode of this light emitting diodes is different than this one, and possibly, actually, let's say for sure this time, is too high for being measured by this type of multimeter. And the reason for this happening is that the technology of this diode is different than this one. This one is a silicon based diode, and this one is probably a gallium arsenide arsenic diode, which is another type of semiconductor, but with a bigger band gap, so a higher built-in voltage. And if we remember the thing we might have said during the course, that in terms of voltage across the p-n junction, we have a corresponding energy that the electron has to have in order to surpass the so-called space charge region. Then if that energy, according to the quantum mechanics, is equal to h, the Planck constants multiply the frequency, the higher the energy, the higher the frequency. The frequency of what? The frequency of the light you see. So 1 over that frequency is the wavelength. It means that if you want to have a wavelength visible in a diode, visible to the human eye, you should have a energy which is higher than the one corresponding to the band gap of the diodes. So for this reason, you need to have a semiconductor with a higher energy band gap before you can see light in a visible range. And this band gap now is so big that it's not possible to be measured by the multimeter. It's not that big, it's probably around 2 volts or something like this, but it's out of the range of this. Okay, so this was just a small digression about LEDs. But let's try to do one thing which is interesting. So let's try to see how a real life component will look like. So in order to do this, now I go here, I close this for a moment, I open a browser, so in a moment I will zoom this so you will better see, but let me first clean the screen. Okay, so if I carefully read what's written on the body of this component, I can read 1N4007. So 1N4007. So what is this thing? For instance, if I take this is a microchip, I can read different numbers. Like here you can read 78A2RRM TL084ACN and the logo. So these are information that the manufacturer put on the electronic devices. So the logo now is, with a little bit of experience, you will recognize it's a logo from Texas Instrument, which is a brand of manufacturer. Then the numbers requires a little bit of attention, because manufacturer of components usually try to write, let's say, the name of the component so you can recognize what it is, plus some other information which sometimes are unknown, or let's say are not so straightforward. It can be, for instance, that they put numbers according to a specific manufacturing lot, other numbers that will specify the type of physical package of the component. So let's say there are numbers which are corresponding to the name of the component plus something else. So one practical thing is to try to put those numbers on Google and see what will come out as a result. So if I put, for instance, now those numbers, because I know what to put, TL084. So then, okay, let me zoom it so you can see better. So you see, I have different options on Google: TL084, TL084A, B, TL08XX. So I have different possibilities. There are all different variations. Let's try to select this one, for instance. So from alldatasheet.com. So this is a real life thing. So we have to know that, for instance, alldatasheet.com, it's a good source for datasheets of components. So you can find many things. So the web page is quite crowded. This is how this kind of web page usually looks like. So full of sometimes useless information. So you have to dig a little bit in order to see what you're looking for. But what we have here, for instance, is a list of datasheets with this number. So they are all the same. And then it proposes you to download a PDF, which seems to be quite different. You see, for instance, this one is 113 kilobytes, this one is 5 megabytes, but the component is the same. So which is the one I need? The answer is it's impossible to know. You have to try and see what you get. For instance, if I click the first one here, now let me zoom a little bit back like this, and like this, and then like this. Okay, here I have a preview of the datasheet. So then you see that this image is kind of resembling the component you have, so maybe it's the right one. So then it tells you that it's a general purpose quadruple operational amplifier. Then you can download the datasheet or click to view. Let's try to click to view. And it opens a sub window like this. You can try to do the same thing on your computer, because you probably see better. So let me try to zoom it back like this. Okay, so here you have it, the description. So, and from now, having this top view of connection, you can start understanding what you have in your hands, if the thing you have is corresponding to the description here. Another thing that you can do is to download the datasheet of the component directly from the place where you bought this component. But who knows where is the place where we bought this component? We find it in our kit. So I know that you might be used to have exact things like in mathematics or whatever, but these technological things unfortunately are not so exact. So they requires a little bit of trial and error things and in understanding what you have, especially because this kit is not let's say a final product, but it's something I mean, somebody put a bunch of components in the box without giving you instruction or whatever. So you have to be a little bit smart in order to understand what you have. But just for trying to understanding how a real datasheet is made. So here we have the first description of the component. Here we can recognize the symbol of an operational amplifier. We have 4 of them inside, so we can use in our circuit. Then what we have is, for instance, here the internal diagram of this microchip, which most of the time is useless, but sometimes it can be useful in order to understand what you have and how it works. So basically in each operational amplifier we have, there is this circuit mounted in a microscopic way, so the microchip inside the body of this component. And if we proceed, we have a lot of tables. The most important tables, which is usually present in every datasheet, is the table of the absolute maximum ratings. So it tells you how not to destroy your device. So for instance here it is telling you that the power supply voltage, which is called VCC, has never to exceed plus or minus negative 18 volts. Then other things, for instance, it tells you T-oper, the operating free air temperature range, and T-storage, which is the temperature at which this device stops working. But the most important usually is this, and the current or the power. Then other things that we can see is a number of parameters that are useful in order to design circuits. For instance, what you can see here is ICC. It tells supply current per amplifier, no load. It means how much current this device draw if you just power up. So it tells you, in this case it's around 1.4 to 2.5 milliamps. Again, it's not an exact value, it comes in a range. You see minimum, typical and maximum values. Usually parameters in electronics are specified like this, and again the reason is according to the manufacturing process they have in the factory. Not all components are exactly the same. They come with a tolerance. So many things. So this current is telling you how much this thing is consuming as current, and this is useful in order, for instance, to understand whether the power source you have is powerful enough to power up this component, or how long this component, this circuit will stay turned on with a certain battery you have, or whatever. So number of data like this. Another important things, for instance, in the operational amplifiers, is this value GBP. It's called gain bandwidth product. It basically tells you what is the maximum frequency that this thing can amplify. So if you amplify signals, signals has a certain spectrum, so frequency domain. So we can amplify slow oscillation or fast oscillation, or combination of slow and fast oscillation, but we cannot amplify whatever signal because there are some limitations inside those components. So this thing is related to this limitation in frequency. At a certain point, after a certain high frequency, it will not amplify anything. So for instance here, it is telling you that something between after 2.5 or 4 megahertz, this thing has a gain. So if you remember, the gain is the amplification factor of the amplifier, which is according to this gain bandwidth product, which is a coefficient that tells you the gain multiplied the bandwidth. So when the gain is 1, the maximum bandwidth is, in this case, let's say 4 megahertz. If we assemble an amplifier with the gain of 2, then the maximum bandwidth will be 2 megahertz. If the gain is 4, it will be 1 megahertz, and so on. So according to the gain you set on the amplifier, you know which is the maximum bandwidth. And for us this is important because when we want to assemble a circuit like this one, for instance, which is an amplifier with a very high gain, and we need this very high gain because we want to measure very weak signals. So easily we can have a gain in the range of 1000. And if we have an operational amplifier with a 4 megahertz gain bandwidth product, it means that the corresponding bandwidth for this amplifier has to be calculated by taking this number 4 divided the gain we set in the amplifier through the feedback resistors. So if it is 1000, then the bandwidth is 4 megahertz divided 1000, and it makes 4 kilohertz. So we can't expect out of a circuit like this to have a signal much bigger than 4 kilohertz to be amplified. Is this good for us in our case? Well, we are on the edge, because we know that a neuron, for instance, will be an event in the time scale of milliseconds, 1-2 milliseconds is the typical duration of an action potential. So if we take, for instance, 1 millisecond as the duration of a neuron pulse, then 1/1 millisecond makes 1 kilohertz. And if these guys have a bandwidth of 4 kilohertz, it's just enough to have a, let's say, kind of good representation of this pulse. So you see how from megahertz we go down to kilohertz. So we think that this amplifier, is super good, it's 4 megahertz. No, it's 4 megahertz if the gain is low. But if we increase the gain, then it's not as good as it seems. And then we have a bunch of graphs which are all interesting for design purposes. For instance, it tells you maximum peak-to-peak output voltage versus frequency, whatever, a lot of things, input current, total power dissipation versus free air temperature. So you have all the characteristics of these things described here. Then you have also some typical application circuits. For instance, here you have examples that are showing you how you can use this amplifier. Other examples, filters, so some screenshots from the oscilloscope. And one, last but not least, an important thing, which is the package mechanical data. So you have the specification of the dimension of this microchip. In our case, it's not interesting because we have the breadboard, but for let's say a person which is designing electronic boards like this one, Arduino, this is interesting because this printed circuit board has to be manufactured according to the dimension of the components. You see here we have many components they have different cases, different packages. For instance, this one is very small. You see this one. So a small mistake in the designing of the so-called footprint of the component then will create a misalignment when you want to solder it on the PCB, and then it will not work. So those package mechanical data are important when you want to actually build a circuit like this. Let's say a professional circuit, I mean something that you can find it in real life. Most of the time nowadays we have a circuit like this, so pre-built circuits, which are called modules. So is in the past, if you want to have a circuit, you had basically three ways, let's say. One was to build it on the breadboard. One was to build it on a so-called Vero board, something like this one. So here it's similar to the breadboard. You can put the components, but you can solder them because these pads are metallized, and you can solder them with a thin alloy. Or you had to build a professional PCB like this one, which still is an option. But nowadays there are a number of these modules. For instance, this is a small power supply, variable power supply, and regulated. You can regulate the voltage by acting on this little trimmer, which is very similar to the one you have, the blue one, in your kit, but is much smaller. Or this one is a battery charger, for instance. So the trend in electronics, which is popular nowadays, at least let's say from the point of view of scientific experimentation or prototyping, let's say for the proper way, is to try to find on internet if you can find a module that implements the function you want, and then you can assemble things with modules together, like this, for instance. Let me see if I have something here that I can show you. I have this thing here. So here I have another Arduino connected with these wires to another board here. And so okay, now it looks like a little bit messy, but if you take advantage of these mounting holes, you can do something, let's say, quite decent just by wiring up different modules. So that's an option if you don't want to create a circuit like this one, which is hard to make it. It requires a lot of time, and it makes sense only if you want basically to create a commercial product, or let's say something that you have to replicate at least maybe 4, 5, 10 times. Like you need many of them in your setup, but for the practical purpose of and experimentation is easier if you take advantage of something that already exists. So basically, what I want to say last is that nowadays the modules are the new microchips. So you can buy things like this and use them directly, and there are so many.